be equal to 1.568 times 10 to the power minus 9 meter to the power 4. Okay, so the conversion is just straightforward. Okay, you don't need to move decimal points. Then we do IZZ2. Okay, so we have 416 cubed over 12 plus by 64, 8.154 minus by 12, okay, squared. So 4 times 16 power 3 by 12, you get 4096 over 3 plus by 8.154 minus 12 squared times by 64 is equal to 946.66 or 67T. Okay, so 4096 over 3 plus by 946.670. So this will be equal to 2.312 times 10 to the power 3 millimeter 4. So this is 2.312 times 10 to the power minus 9 meter 4. Okay, so finally we know our IZZ. So IZZ is equal to 1.568 times 10 to the power minus 9 plus by 2.312. Okay, so 1.568 plus by 2.312. So it's 3.88 times 10 to the power minus 9 meter 4. Okay. So the next thing is we want to find our stresses. Okay, so I'm going to copy this whole diagram so I don't shift a lot. Okay, the diagram did not follow. Oh, I think I have to do the whole thing. Yes. Right. So now we are going to find the stress. So this is point A, right? And that's point D, right? So the formula that we're going to apply is stress X is equal to Px over A minus by Mz over Izz multiplied by. So this is the general solution. Okay, I'm writing down here that this is our general solution. Not solution, formula. Okay. So if you look at textbook, this is the formula that you get. Okay. So we know that we are looking for Px. So Px, we know that it's going to go through compression. So Px is equal to minus 400. Area we found, okay, so area on the table we found is equal to 104. Okay, 104 millimeters squared, or 104 times 10 to the power minus 6 meter squared. Okay, so from here you can, so not yet, so we also know our mz is equal to p. So p is equal to 400 multiplied by 50 times 10 to the power minus 3 plus by 8.154 times 10 to the power minus 3. Okay, so this will be equal to 50 power, so 50 power minus 3 plus 8.154 power minus 3 times by 400, so it's equal to 23.262. Okay, 262 Newton meter. So we also can calculate Px over A. So this is equal to minus 400, right? is it minus or plus? I don't know why I put minus. Wait, sorry, it's plus. Okay, it's not minus. Positive. Divide by area, which is 104 times 10 to the power minus 6. So 400 divided by 104 power minus 6 is equal to 3.846 times 10 to the power 6 Pascal. Okay. So the first thing we're going to do is we're going to find stress X at point A, right, where Y is equal to 8.154 times 10 to the power minus 3 meters. Okay. So stress X at point A, right? So this will be equal to Px over A. We know that it's equal to positive 3.846 times 10 to the power 6. So from here, we know that at point A, right, it is going to be at tensile. So it's positive, right? So MZ, we know is 23.262. Divide by IZZ, we found IZ is 3.88. 10 to the power minus 9, and this is equal to 8.154. So no need to worry about the 8.154, is it positive or negative. We know that this is going to be what? Tensile, based on analysis, right? So 23.262 times 8.154 power minus 3, divided by 3.88 power minus 9, plus by 3.8446 power 6. So this is equal to 52.732. Positive 52.732 times 10 to the power 6 Pascal. I do again 3.846 power 6 or 23.262 times 8.154 power minus 3 divided by 3.88 power minus 9 plus by 3.846 power 6 is equal to 52.732 times 10 to the power 6 Pascal. Okay. So next we want to calculate stress X at point D. So we know that Y is equal to 11 point what is equal, we calculate 11.846. Okay, it's equal to 11.846 times 10 to the power minus 3 meters. Okay, so from here we can calculate our stress at point D. Okay, so stress X at point D. So the axial load is still going to be tensile. Okay. Now this will go into compression because we know at point D, right, is at the head of the bending moment vector. It's going to be negative. So this is equal to 23.262 multiplied by 11.846 times 10 to the power minus 3 divided by 3.88 times 10 to the power minus 9. Okay, let me write this out. 3.88. 3.88. So this will be equal to positive 3.846 times 10 to the power 6 minus, okay, 23.262 times 11.846 power minus 3 divided by 3.88 power. So it's equal to 71.021 times 10 to the power 6. So this is equal to 3.846 power 6 minus 71.021 power 6 is equal to minus 67.175 times 10 to the power 6 Pascal. Okay. Why I wrote these two numbers out, so you can see for yourself, this is due to the axial load, right? And this is due to the bending moment. So from this example, you can see that the bending moment magnitude is significantly higher than the what? Axial loading. Okay. So the last part of the question they asked us to find, okay, and I'm going to show you two ways of finding this. Okay, I'm going to show you two ways of finding this. So the first way is you apply the generic formula. Okay, not generic, what the general formula, okay? So we know that stress X is equal to Px over A minus by mz over Izz multiplied by y, right? So I'll start in a new page, okay? This is like foolish of me. Okay. So what we're gonna do is we're gonna find the position, find the location of the neutral axis. Okay, so we're going to apply this formula, right? We're going to apply this formula. So this one, what we're going to do is we're going to find y when stress X is equal to what? Is equal to 0. Okay, so from here, this is 0. Px over A, we had our Px over A value, right? It's 3.846 times 10 to the power 6. 3.846 times 10 to the power 6 minus by mz. Okay, so mz, we know our mz. What was our mz? I can't remember. It's 23.262. Okay, 23.262 divided by our Izz, which is 3.88. Okay, 3.88 times 10 to the power minus 9, and this is your y. Okay, so one equation, one unknown, is easy to find. So y is equal to 3.846 times 10 to the power 6. Now multiply 3.88 times 10 to the power minus 9 divided by 23.262. Okay. So this will be equal to 3.846 power 6, 3.846 power 6 times by 3.88 power minus 9 divided by 3.262 is equal to, I get 0.64 positive, 0.6415 times 10 to the power minus 3 meters. Okay. Now, what does this positive actually means? Okay, what does this y positive actually means? So again, you have to go back to analysis. Okay, so if you look at our structure, the way it's deformed is deformed this way, right? Yeah. The way the structure is deformed this way. So like what I taught you last week, right? If this is our centroid, right? Over here, this is our center of curvature, right? So i.e. y positive is in this direction, right? Y negative is in this direction. So this means y has been shifted what? Downwards. So be really, really careful with this, okay? I will propose, can we go for a break? You all need a break or you're okay? A break? No reaction. Okay, so what I propose is we go for a 15 minutes break. We come back. I show you a easier way. It's just drawing graphs, okay? And we just solve it. Then you can physically see what's going on, okay? So we go for a break. We come back at 8:45, okay? Thank you.